Okay, in this video, we're going to talk about weak bases. If you missed our previous lectures on strong acids, strong bases, and weak acids, please go back and watch those because we're going to use a lot of that knowledge we built up in those lectures in this current video. So let's talk briefly and introduce the concept of weak bases. So just like we talked about for a weak acid, it's really built on this concept of a weak electrolyte, something that, in an acid, a weak acid is something that doesn't dissociate completely. And so it's a matter of this equilibrium process. So if we want to consider a base, we'll call it just B here, and it's in water, an aqueous solution. Here's the water, H2O. It's not going to be a one-way arrow like a strong base would be, donating completely OH minus. It's an equilibrium arrow. And what does a base do? Remember, for an acid, it was all about donating an H plus and creating hydronium H3O plus. But this is a base, right? Here, what a base does is it accepts a proton. So it's taking the proton. Here, water is the acid. Water donates its proton, and so you end up getting HB plus, right? The H plus right here coming from the water. So this is now HB plus aqueous, and what's left of the water, where water lost its H plus, so it's OH minus. Okay, and thus this meets the definition of the base. We have OH minus being created. The base is the proton acceptor. Water here is acting like the acid. Now, everything we learned about weak acids applies. You have a dissociation constant. Here it's not an acid dissociation constant, Ka, but of course a base dissociation constant, Kb. And we still write this the same, products over reactants. So here it's going to be our Hb plus concentration at equilibrium, of course, multiplied by our OH minus concentration at equilibrium, of course. Those are the products over reactants, the base concentration at equilibrium, and no need to write water down here since it's a liquid. We only write the aqueous things here in our base dissociation constant. So, whereas acids, we had Ka, and we were concerned with H plus, aka H3O plus. Here for bases, of course, we're concerned with Kb's and OH minus. Acids, we were talking about pH. Bases, we usually talk about pOH. Although you might be asked to calculate one versus the other, and that's okay because we know pH and pOH are related. They add up to 14. Okay. We said for acids, the larger the Ka value, the stronger the acid. So the same is said here, the larger the Kb, larger the Kb, stronger the base. Okay, so this summarizes a nice introduction to weak bases. Let's look at a prototypical weak base, NH3. This NH3, if that's our base, when it's in water, there's going to be an equilibrium where the NH3 accepts an H+, so we make NH4+, ammonium ion, plus OH minus. This weak base, ammonia, this is our weak base. Water is acting like the acid. This would be our conjugate acid of our weak base. This NH3 has a Kb value. This is the base dissociation constant. And so everything about determining the pH or pOH of a weak base is going to be about establishing the equilibrium concentrations. So we're going to use ice charts, ice tables, much like we did in our Ka weak acid dissociation problems. right? So here's the actual representation for this weak base ammonia. There's our Kb. And these weak bases usually will have a lone pair of electrons that lets them accept this H+. So that's one way we might have a weak base, like NH3 here. If you drew out the Lewis structure, of course, this NH3 is trigonal pyramidal with this lone pair of electrons. And that is what accepts the H+ and creates then a bond with that hydrogen. Now, weak bases might also be identified as being anions of weak acids. So remember our notion of conjugate acid, conjugate base, these pairs, conjugate acid base pairs. If you had a weak acid like HF, which creates H+ and F-, this is what we're talking about right here. This F- would be a weak base. It's the conjugate base of this weak acid. It itself is then a weak base. So this can be a weak base, or something with a lone pair of electrons can be a weak base. Now, let's try a calculation as an example where we look at taking this information for a base and calculating the pH of this weak base solution. You can try to work ahead and work this out yourself. Pause the video here if you would like to do that. Otherwise, I'm going to proceed and solve it. So first thing we always do in these problems is write the equation. And sometimes, you might be used to working on Ka problems or just have that in your mind that you have to write something as donating a proton and acting like an acid. But just take stock when you read a question for the first time and identify, is this an acid or a base? And H3 is our prototypical weak base. And so we need to make sure we're writing the right kind of reaction. A common mistake students will make is write NH3 here and then have it donate a proton and act like an acid. All right, so make sure we are identifying whether we're dealing with an acid or a base so we get this equation correct. If it's a base like it is here, then we should see an OH-. Okay, if it's an acid, we should see an H+ or H3O+. So make sure we have the reaction right here. It looks just fine. Our Kb expression we're going to write out, keeping in mind these are all equilibrium values. And this necessitates then, if we want to calculate a pH, we're going to have to write an ice chart here. Okay, this would be my NH3, my H2O. It's liquid, doesn't factor in. My NH4+, my OH-. So sometimes this is called a Rice chart because I like to write the reaction at the top before the initial change in equilibrium. All we're told here is it's a 0.15 molar solution of NH3, which means there's zeros here. Now, we're not told anything else about the equilibrium values, so we have to look at this and realize that the products, if they're starting at 0, must go up. And they're going to go up by some amount we'll call x, so plus x plus x. If the products are going up, the reactants are going down, so here's a minus sign. And stoichiometry dictates this is all 1-to-1. The reaction is balanced. There's a 1 here, a 1 here, a 1 here, and a 1 here. So if the reactants, if the products are going up by x, then there's a 1-to-1 ratio here. The reactants are going down by x. It's not going to be plus 2x and x or x and minus 3x because it's all a 1-to-1 ratio. And so my equilibrium values 0 plus x, that's an x, 0 plus x, that's an x, 0.15 minus x is the value here. Okay. Now, I'll show that here a little bit cleaned up. We have our KB. Our KB value is 1.8 times 10 to the negative 5. So I know this is going to equal, as I've written it here, NH4 plus, that is X. OH minus, that is X. So X times X is X squared. Products over X. Reactants, 0.15 minus X, right here. And now I can rearrange this and solve with the quadratic formula, or I can remember this assumption I taught you in the previous video, that you can try to save a bunch of time, and you should, by neglecting this X. Just make sure you check the assumption later, which we will. So if we neglect this X, this equation, of course, simplifies to just X squared over 0.15, and now I don't have to get the quadratic formula involved. I multiply both sides by 0.15, this times 0.15, and it'll drop out here. And I'll be left, after rearranging and taking the square root of the result, that X equals 0.0016. Again, that's 1.8 times 10 to the negative 5 times 0.15, and take the square root of the result. That gives me my X value here of 0.0016. Now, remember, we have to check this assumption. How do we know if neglecting X was fair? Well, it's if X is really small, and it should be small if it's a weak acid or weak base. It doesn't dissociate much, or the equilibrium doesn't lie very far with the products. It's mostly reactants. So you don't have a lot of this around, and this stuff is our X value. So if it lies mostly with the reactants, which a small K value suggests, then this X is probably pretty small and can be neglected. But we'll test it for sure by doing the following. Is this 0.0016 less than 5%, we'll say 5 over 100 times, 5% of my initial NH3? And when we'll see here, 0.0016 is indeed less than 5 times 0.15 over 100 is 0.0075, and 0.0016 is less than 0.0075, so that was safe to do. And now that we have X, we realize that this X value is indeed my OH minus concentration. So to get the pH, realize that we have POH. We need to take this X value that represents our OH minus at equilibrium, and I need to convert that into H plus before taking the negative log. Or I simply take the negative log of this and realize 14 minus that is the pH. Okay, go back and watch the previous videos if you want more clarification on that. But this is the rest of the algebra we've done here to identify this X. It was indeed less than 0.0075, so that was safe to do. And note this is the molarity now of my OH minus. So taking negative log of that gives me a value of 2.80. So another common place in weak base problems students will mess up is they'll take the negative log of this X value, because they're so used to doing it for acid dissociations, they'll take the negative log of this 0.0016, and they'll say, this is 2.80. Aha, this is the pH, I'm done. Right? But that's wrong, this is not the pH. Remember, this P stands for negative log of, so pH is negative log of H plus. What you're taking here is the negative log of OH minus. So this is really the POH. And if the problem asks you for a POH, good, you're done. But it didn't. In this case, we were asked for the pH. We remember pH plus POH is always equal to 14. Therefore, to find the pH, it's 14 minus this 2.80. And that's what gives us our final answer. pH is 11.2. Now, have the conceptual check at the end. Get in the habit of doing the following. Go back and reread the question. the pH of a weak base. Well, the pH of a weak base below 7 is acidic, above 7 is basic. So a pH of a weak base should be above 7. And it is 11.2, so that looks good. Doing this conceptual check at the end will prevent you from reporting this as a pH 2.8 because that looks really acidic. So either we messed up the math or this isn't really the pH. And it's not the pH, it's the pOH. Okay, so this is this example calculating the pH of a weak base with its base dissociation constant. Now, let's talk a little bit about this Kb further. We saw that pH plus pOH is 14. There's a similar type of relationship between Ka and Kb. Ka times Kb equals Kw. And at 25 degrees Celsius, this Kw is 1.0 times 10 to the negative 14. So there might be some times in problems where you have to use this equation, Ka times Kb is 1 times 10 to the negative 14, to solve for a Ka or a Kb. So, for example, in the previous problem, I could have been given this, right? I could have been given the Ka of NH4+, but the equilibrium I was worried about was for NH3, so I have to find the Kb of NH3. And I can do that by plugging this in for Ka, 1 times 10 to the negative 14 in for water, and solving for Kb, where I will get 1.8 times 10 to the negative 5 before using that in my products over reactants equilibrium when I'm plugging in those values. Now, we can actually derive and show where this formula comes from with a quick example, right? We can write down NH4+. This is the conjugate acid of this base. So thinking about this conjugate acid equilibrium, what does an acid do? Well, it donates its proton to make H+, right? And there's a Ka associated with this. It's a Ka because it's an acid. At least how I've written it, the reactant is an acid here. Now, for NH3, what does NH3 do in water? Well, it's a base, so it accepts that proton to make NH4+, and it creates OH-, and there's a Kb associated with that. And now think back to our previous lectures on equilibrium, where we talked about manipulating equations and how that affects equilibrium constants. Let's try to add reaction 1 and reaction 2 together. When we add these two reactions together, we see an NH3 on both sides, that cancels out. We see an NH4+ on both sides, that cancels out. And what we're left with here is H2O in equilibrium with H+ and OH-, which is exactly our sort of autoionization we talked about before. And there's a Kw associated with this, products over reactants. Remember, when we add reactions together, what do we do to their equilibrium constants? When we add reactions, we multiply their equilibrium constants. So Ka times Kb is what gives us Kw, and that's the formula we've given right here. Okay, the point is, if you know Ka, you can solve for Kb, because you always have in the back of your mind this Kw value, at least at room temperature. If it's a different temperature, you might have to be given Kw at that other temperature. In some cases, you might just have to assume 1 times 10 to the negative 14. And that's a number you should memorize. Okay, so let's put some of this all together and try this practice problem here, where we calculate the pOH of a solution of propionic acid, given a Kb of propionic acid, as 7.7 times 10 to the negative 10. Okay, so in these problems, we like to read through them once, which we just did, and read through them again. Identify this is probably an equilibrium type problem, right? We have the concentration, so 0.095 molar. This is my initial concentration. This is my KB. I just like to write these values I'm given sort of succinctly down somewhere. And I'm after the POH. The first step in all of these problems is always write the reaction. Okay? If you'd like to write the reaction and give it a shot, and then even try to proceed and solve this problem, feel free to do that now, pause the video. Otherwise, I'm going to proceed and show you how to do it. Okay, students get really confused in writing this because we've just been talking about weak bases. So this, if you don't do the reaction correctly, you have no hope of solving this problem. So really take the time to think about what is the reaction. Okay, this is propionic acid. This is an acid. It is not a base, it is an acid. So what do acids do? They donate a proton. That's the reaction. Now I can, given that reaction, draw my Rice chart. And start to solve the rest of this. Another thing we like to do here, of course, is write after the reaction and maybe laying out our ice chart, write the equilibrium constant for this process, okay? It's going to be products over reactants. And this is an acid, so this equilibrium that I'm concerned about is a Ka. This right here is a Kb. Tricky. I can't plug this value in for here because it's not a Ka. I need to take this 7.7 and convert it into a Ka. I can do that now or later. We can just do it now. That's fine. We know that 1.0 times 10 to the negative 14, Kw, is Ka times Kb. And so if I want to convert this to a Ka, I take that 10 to the negative 14 and divide it by this Kb. And so here my Ka comes out to 1.3 times 10 to the negative 5, and this looks like a decent Ka value. We've seen numbers and exponents like this for our weak acid Kas, so that looks good. So that's ultimately what I'm going to take and plug into here. But I also need these equilibrium values, and that's where the ice chart comes in. So let's take a look at our ice chart. Let's see what we were given at the start, 0.095 molar. That's my initial, so that goes here. There's nothing at the start here, so those are zeros. If these are zeros, they must go up by some amount x. Everything's a 1-to-1 ratio, so if these go up by x, this goes down by x. And now we have everything we need. We can write our Ka here that we solved for, 1.3 times 10 to the negative 5. That's going to be x squared. This times this over my equilibrium here. I can now try neglecting the x. So this equals x squared over 0.095. I'll check that assumption later, of course. But now this is easy to solve. Right? I've just written this over here to make it more clear how I'm going to solve this. Multiply both sides by 0.095 and take the square root. My x value I'll get as a result here is 0.0011 molar. Is that less than 5? Checking our assumption here, I'll do this in blue. Is this less than 5% of the original? And yes, it is. 5% of the original is 0.004. 0.001 is less than that. So this is a safe assumption. And again, be careful with these x's at the end. Remember, this x at the end represents my H plus concentration. So this is my H plus concentration at equilibrium. What am I asked for? Ultimately, I'm asked for POH, which is a little confusing for an acid, but it's something you could be asked for. So I know taking the negative log of this gives me pH, and I'm going to have to then subtract that number from 14. So negative log of this number is my pH. That is 2.959, which means my POH is 14 minus 2.959. And thus my final POH here is pretty close. We'll just round it to 11. We can have the conceptual check. We know for a weak acid, we should get a pH less than 7, we did, and a POH greater than 7, which we did. Okay, so the final answer here again should be POH equal to about 11. Okay, so this problem in particular was made kind of tricky and as confusing as possible, giving you an acid, but pairing it with a KB, asking for a POH, right, to try to misdirect you to think of it as a base, but really it's an acid. It says acid right there in the name, so be very careful when you're starting this, you're writing the correct reaction, and let that sort of drive the bus of how you're solving the problem. Once you realize it's an acid here, I need to work with Ka. I'm going to be taking a negative log of the x to get a pH. Just make sure we're converting that pH to a POH at the end. So in this video, we talked a lot about weak bases, but here at the end, we showed you an older type of problem as a weak acid, just bringing in this new information about the base dissociation constant and POH and how we can manipulate these things. So in the next video, we'll check out different types of acids like oxyacids and carboxylic acids. But that'll do it for this lecture. See you next time.